In this video, we'll show you how to remove, replace, diagnose, and repair an alternator from a Toyota. The basic design of an alternator is almost the same for all internal combustion engine cars. So this procedure can be applied to almost all internal combustion engine cars, not just for a Toyota. First thing we're going to do is to remove the alternator. This one is from a Toyota Matrix 2006 model, but it will be the same for between year 2003 and 2008. Same for the Corolla model and Pontiac Vibe. First thing we're going to do is to remove this connector right here. You just press at the end here and then you pull it straight out. First thing we're going to do is to remove the fan in order to have enough room to work on an alternator here. And I already removed the fan, and it's quite simple to remove. One bolt right here, one bolt right there, and then you just have to disconnect the cable that goes into the fan. Press this down and it can pull straight out. Now I have a lot of room to work on the alternator when the fan is removed. Next step is to remove this thick cable here. It has a 10mm nut that you have to remove. This is the main positive cable that goes straight to the main positive terminal of the battery, and it is the output from the alternator to charge the battery. I'm going to use electrical tape and tape this up to prevent it from touching the body of the car. It will short out, and that way I don't have to disconnect the battery. Next, we need to disconnect this one. Use a flathead screwdriver, put it in there, push it out, and then push the connector out, just like that. Next step, I need to release the tension of the belt. And before I do that, I made a little artwork just in case the belt slips out. Yep, Picasso would be proud. There are two bolts down here in this corner. There's one bolt on the top, there's one bolt on the bottom. This top bolt is the bolt that you need to release. The size is 19mm, and you need to turn this bolt clockwise. It's all the way down there, so not to reach the bolt, I have a 19mm socket with a ratchet and a pipe, so that will give me more leverage. Now we're just going to turn it clockwise, meaning going down. Now the belt is loose and I can release the belt just like that. And that's what it looks like. Just leave it like that. Do not remove the belt, and it will make your job a lot easier when you try to put it back. It's time to remove the alternator. There are two bolts that hold it to the chassis of the car. Top bolt is 12mm right here, and the bottom bolt is right down there, and it's 14mm. That's where it is. Here's top bolt. Here's a 14mm nut. It's quite long. Now I got the two bolts removed. You can see I'm able to rock it back and forth. In order to remove this alternator, you just have to pull it straight out this way. Sometimes it's quite hard to remove the alternator. You just try to wiggle it out. This part of the alternator, it grabs onto the chassis of the car like this, and sometimes it's quite tight because it's been in the car for so long. So all you have to do is just use a pry bar, put it in here, and just pry it out, and it should come out. So here's the alternator. I'm going to remove the top cover so you can see the inside. We just have to remove 3 nuts. 1, 2, 3. These are 8mm, and there's one more 10mm nut right here. Here is the inside of the alternator. We have 3 main parts that are removable and you can remove them for bench testing. We got the voltage regulator, which is this part right here, and this is the same part that I salvaged from a different car of the same model. We got the payout brushes, which is this part right here, and we have a diode bridge rectifier, which is this part right here. Among these three parts, you can bench test the brushes, the diode bridge rectifier, but you cannot fully bench test the voltage regulator. This part here, you can partially bench test it, but in order to fully bench test this part, you're going to need a special equipment, which is quite expensive, and that's what I don't have. But the good thing is all of the other parts on this alternator can be bench test, all of them, including the brushes, the rectifier, the rotor, and the stator. And if everything tests out good and your alternator is still not working, then we can safely deduce that the voltage regulator is bad, even though we don't have the right equipment to fully test this part. So next I'm gonna hook it up and show you how to bench test the entire alternator. There are only 4 wires that you need to hook it up to bench test this. We got the negative terminal, which is ground, that goes to the body of the alternator, and that goes to my battery negative terminal. The next wire is from here that goes straight to the positive terminal of the battery. This is the main positive that goes to the alternator. You can tell because when I removed this alternator, this was hooked up to a very thick wire that goes straight to the positive of the battery. The next 2 wires goes from the regulator to the battery. This connector here on the regulator, it has 3 pins, and there's a connector that plugs into it that has 3 wires, 3 different colors, white, red, and yellow, and that wire is on the car. The white wire is positive 12 volt that goes to the battery. The red wire is the ignition switch wire. It only turns on when you flip the switch, the key on the ignition. The yellow wire is the LED battery light on the dashboard. The yellow wire is the LED battery light on the dashboard. And this wire is only on when the battery is low. Here is the position of the connector that corresponds to this picture. So now on this connector, I have the white wire that goes straight to the positive terminal of the battery. I've got the red wire that goes to the middle pin. That is the ignition switch pin. And it's not connected yet. I'm going to connect it to the battery to simulate the ignition on. Now we measure the voltage between the 2 brushes, which is between this pin here on the screw and this pin here on the screw. And we got 11 volts, which seems to be good. The battery voltage is 12 volt right now, and the alternator is not spinning. So 11 volts is reasonable. I'm going to go ahead and flip it so that I can spin the pulley with my drill, and my drill can do about 2000 RPMs. So at 2000 RPM, it should be able to charge my battery above 13 volts, at least 13 volts or more. If it's not charging my battery, that means that there's something wrong with the alternator. By the way, this bolt here is 10 millimeters. Here we go. It's not charging my battery. As you can see, it's not charging my battery at 2000 RPM. So that's definitely something wrong with this alternator, and that's what we need to figure out. Let me tell you a secret about a very common problem with all of these alternators, and that is the brushes. All of these alternators use brushes, and it should be the very first thing that you should test, and this is very easy to test. And I would say a majority of problems with all these alternators are related to worn out brushes. This is very easy to test, and you can figure it out in less than a minute with your multimeter. That means you can figure out the problem with almost all alternator in less than a minute. Set your meter to continuity test. So if the two wires touch, it will beep. So this one has two brushes, one on the top and one on the bottom. The top brush corresponds to the screw mount on the right here. So if I touch, it will beep. The screw mount on the left corresponds to the bottom brush, like that. And because the two brushes touch the two slip rings on the shaft of the rotor, what you want to measure is, imagine my finger here is the rotor shaft, and it has two slip rings, right? One on the top that contacts with the top brush, and one slip ring on the bottom that's in contact with the bottom brush. You want to measure the continuity between this and the top slip ring and this and the second slip ring. So between this and the top slip ring, it has to be continuous, and this to the bottom slip ring has to be continuous. Let me demonstrate. So between here and the top brush, it's continuous, but between here and the top slip ring, which I'm going to put on this side, it's not beeping, so it's not continuous. Let me try on this side here. So on this side, it should be the bottom brush. So I measure from this point here to the bottom slip ring. You see it beeps. That means it's continuous. So the brush is touching the slip ring on the bottom, but not the slip ring on the top. Let me try this again. This should be continuous to the top brush, and that should be continuous to the top slip ring, and it's not beeping. That means this brush here on the top is too worn out to a point where it's too short to touch the slip ring, and therefore it's not continuous between here and the slip ring anymore, and therefore there's no power that being sent to the rotor from the regulator anymore. The regulator sent power to the rotor via the two brushes and the two slip rings, and they have to be continuous. And if there's a disconnection between the brush and the slip ring, power is not being sent from the regulator to the rotor anymore, and therefore there's no power in the coil of the stator, and therefore there's no power that goes to the battery anymore. I'm going to remove the brushes on here to check it out, just to confirm. And it's very easy to remove all of these parts here on the top here. 1, 2, 3, 4, 5 screws, and everything will come out. All the screws are removed. Now we can just pull everything out. For the bridge rectifier, you have to remove more screws down here. I'm going to do that in a little bit. But right now, let's take a look at the brushes. Just as I predicted, you can see how worn it is, especially the top brush. We got about, let's say, 2 millimeters sticking out. The bottom brush is a little bit better. I think that's about 3 to 4 millimeters. The top brush is quite worn, and it's not touching the slip ring on the rotor anymore. Here you can see the two slip ring, one ring on the top, one ring on the bottom, and it's not touching the top slip ring. And that, I think, the problem with this alternator. Could be other problems. I'm going to go ahead and test every single components in a little bit. Now let's compare between my brushes with another brush set from a different car and see how long it is compared to my brushes. And these are used brushes. They are not new. New ones should be even longer, probably all the way out here. And that's about, let's say, 40 to 50% left. That's completely worn out, and to a point it doesn't touch the slip ring anymore. Go ahead and put this new set of brushes in, and I'll do a test again to see if it works. But first, let's try and do a continuity test with my new set of brushes. This here with the top slip ring, there we go, it's touching, therefore it's beeping. This one should go to the bottom slip ring, there we go, so it's working. Alright, let's try this again. Spin this up. You see the voltage is decreasing. As I speed up, the voltage starts to increase. 13 volts right now, and we get 3.8 amps. 3.5 amps. So there you have it. It's working great. When I spin up my drill, I can feel a lot of resistance going through the drill. And before, with the bad brushes, it just spin at very fast maximum RPM. I didn't feel any resistance at all. But this time with the new brushes, the RPM at max speed is much slower, and there's a lot of resistance. So that's how you fix an alternator, folks. Very easy. Most of the time, it's just replacing the brushes. So for this particular alternator, I can just stop here because I already fixed the problem. But an alternator has so many parts and many other things can go wrong. So what if the problem is not your brushes? What if something else? And that's what I'm going to show you next. I got my diagram here, and I'm going to show you how this works and how to fix every single component of an alternator. In order to repair every single component on an alternator, we need to understand how it works first. This is a typical diagram for an alternator for most older cars. I'm going to start from the battery first. So the battery sends 12 volts to the regulator, but it's not on yet. There's a key in the ignition, and if it's off, then the whole system is off until you turn on the key on the ignition. Now it receives a signal from your key ignition. It will turn on and sends power to the rotor, to the brushes, and then to the rotor. Now the rotor is energized. When you start the car, it will spin the rotor, and it will create a magnetic field. And that magnetic field will induce a current through the stator. I'm drawing the rotor outside of the stator for you to easily visualize it, but the rotor is actually inside the stator and is spinning inside the stator, as you can see on here. So that's the shaft of the rotor is spinning inside. There's a coil on the rotor, and the stator is on the outside. The magnetic field on the rotor induces a current on the stator, but that current is AC, or alternating current. So it has to go through this set of diodes in order to turn into DC to charge your battery. Now that's generally how it works in a short summary, but I'm going to go into details of why it is used the way it is. Like, why don't we use a permanent magnet here? Why do we use electromagnet? And why do we have 3 phases here? And why do we have a diode bridge rectifier here? So first let's talk about the rotor. This is an electromagnet. It's not a permanent magnet. So why don't we just use a permanent magnet, right? And that's because your engine RPM, it varies. When you are idle, it runs at low speed, but when you drive on a highway, for example, the RPM is higher. Therefore, it's variable. It's not constant. At lower RPM, you might be fine, right? The output here could be 14 volts to charge a battery. But at maximum RPM, the output on the alternator could go up to 200 volts. And that for sure will destroy your battery and your car computer in a very short amount of time. So with an electromagnet, the voltage and current output of this rotor is controlled by the regulator. So when your vehicle runs at higher RPM, it will reduce the voltage and the current output so that the magnetic field that's inducing a current here on the stator is lower and is always 14.5 volts instead of 200 volts. Next thing we're going to talk about is the stator, which is the stationary part of the alternator. On the actual alternator, you can see the coils through the holes here, and that's the coil that runs on the outside of the alternator. The rotor is a coil that's in the middle and spins around in the middle. But why does the stator have 3 coils? And why does it have a very weird star configuration that looks like a letter Y? Now let's assume that we have 1 coil on the stator. I'm going to cover this up with a piece of paper. As the regulator puts out a current through this wire here, through the brushes, it induces a magnetic field. And this becomes a magnet. So let's assume this is the magnet that spins around the stator. As the magnet spins closer and closer to the coil, the current that's induced by the magnet to the coil gets stronger and stronger, and it will get to a maximum point right here. So if you take a voltmeter and measure the output right here on the coil, you're going to see the voltage that goes from 0 and it starts to rise up to the maximum point where the north pole reaches the center of the coil. As the north pole moves further away from the coil, the magnetic field gets weaker and weaker, and up to a point where we don't see it anymore. And if we look at the voltmeter, we're going to see a continuous decrease of the voltage output until it gets to 0. So at this point, it doesn't see any magnetic field from the north pole anymore. And that's why we see 0 volts. But then as it continues to spin, you see the south pole starts to approach the coil, and therefore it starts to induce a current through the coil. But because the magnetic field on the south pole is the opposite of the north pole, and therefore the induced currents is the opposite of the north pole. And on the multimeter, you're going to see the voltage start to increase, but then it's negative to a point of maximum right here where the south pole reaches the coil right in the middle. And then as the south pole moves away from the coil, the signal gets weaker and weaker and weaker to the point it reaches 0. And that's what we see here on this graph. It gets weaker until it gets to 0. But then it continues to spin, and then the north pole starts to approach the coil and starts to induce a current. And the current gets stronger and stronger until it gets to this point. And this is what we're going to see on the graph. Current gets stronger and stronger and reach maximum right here. And then the cycle continues, and it will be like this on the output. And that's what we call AC, or alternating current, because the current is always changing. In this case, we only have 1 coil. As the north pole spins further and further away from the coil, the magnetic fields get weaker and weaker until it gets to 0. And it doesn't have any signal until it gets closer to the coil to about this point here. So between this point and all the way around till here, we don't have any signal, and it doesn't produce any current for the north pole. And that's why, in order to utilize the downtime of the magnet as it spins around the stator, we introduce more coils on the stator. So in this case, as the magnet spins, it gets weaker and weaker from the first coil, but then it's approaching the second coil, and the signal gets stronger and stronger and gets maximum on the second coil right about here. And then it gets away from the second coil, so the signal gets weaker on the second coil, and then it's approaching the third coil. So for one single round, it produces 3 different electrical currents. And that's what we see in this graph. We have 3 different AC current outputs. Each is offset one another by just a little bit. And that's because the timing is different as the rotor spins around the coil. As the rotor spins, it gets to peak voltage right here on the first coil, and that's what you see right here. but it's going to take some time before it gets a peak voltage on the second coil, and that's what you see right here. It's offset by just a little bit because the timing is a little bit different, and it takes some time for the rotor to spin to get to this point where it gets a peak voltage on the third coil. That's what you see right here. If you combine all three coils together to get the current output out to a single point, you're going to get something like this. So this is a combined current of all three phases of the AC output, and that way you can maximize the efficiency of the rotor as it spins around the stator. But now with the AC output, we have a few problems. First of all, your battery is DC voltage, and you cannot use AC to charge a DC battery. And second, when your AC output is negative below zero, so at this point, when the voltage output is below zero, it's going to discharge the battery instead of charging the battery. And that's why we use diodes, to allow the current to flow only in one direction and not the other. And so the three diodes down here to block out the current that goes back to the battery. And the reason why we got three diodes is because each diode is responsible for each phase output on the stator. And the other three diodes on top is again for blocking the current flowing back to the stator, either because there's a fault in the system or when the engine is off. The power from the battery continues to flow in the system, and it flows back to the stator when the engine is not running. At this point, the current output is still AC, but it ripples up and down, and it's not very stable. So to smooth it out, we're going to use a capacitor, and at the end, you're going to get a straight line DC current at 14.4 volts. And that is the basic inner working of an alternator. And now that we understand the inner working of every single component on an alternator, it's very easy to diagnose and fix every single component on it. So previously I showed you how to diagnose the regulator and the brushes. The next component on the alternator is the rotor, which is this part right here in the center. I just removed the regulator and the brushes so you can see clearly the rotor shaft here. What I'm going to do is to measure the resistance on the winding of the rotor to make sure that it is normal range and there's no cut on the wires of the rotor. These 2 points here on the rotor are the 2 slip rings on the shaft of the rotor. And that's this ring right here on the top and this ring right here on the bottom. Put your multimeter to ohm, and if we measure it, you're going to get about 2.5 ohm. The normal value is between 2.5 to 3 ohms. The rotor winding is free floating, it's not connected to ground. So I want to make sure that it's not shorted to the body of the alternator. So I'm going to put it on continuity test. So when this touches, it will beep. The center of the shaft is ground. So I also want to make sure that it is connected to ground. And now I want to make sure that the winding is not connected to ground. That's not connected, and that's not connected. So the rotor has normal value and it works fine. The next thing I want to test is a stator, and it's connected to the diode bridge rectifier, as you can see here, this part. And I have to remove this part in order to get to the stator winding. There are only 4 screws on the diode bridge. I've got all the screws out, and this part will just come out just like that. Very easy. We got 4 poles that are sticking up, and they are connected to the bridge rectifier, and in which 3 of them are the ends of the stator winding, here, here, and here. The 4th pole, which is this pole right here, is where all the windings are connected together, right in the middle right here. So this point right here where I have my red tape is this point right here. The stator windings are actually assembled in pair, As you can see through the frame of the alternator, you can see two wires that are connected to the poles up here. So there are actually three pairs of windings instead of single winding, as you can see on my diagram right here. But I just want to simplify the diagram to make it easy to understand. The testing procedure is all the same. You want to make sure that all the windings on the stator are connected together at the midpoint, and all the windings are not connected to ground. I'm going to put my meter to continuity test and make sure all the poles are connected together like that. Now I want to make sure all the poles are not connected to ground. So one probe to the case of the alternator and the other probe to the poles. No beep, that means it's isolated from ground. So the stator windings are all good. My next test is to test the diode bridge rectifier. First of all, let me show you how to test a diode, which is a device that only allows current to flow in one direction. You can see the yellow band on the right side of the diode, which represents an arrow in this direction. So I put my multimeter to diode and put my probe on the positive on the left side here and negative on the right side. You see we got about half a volt. And if I reverse the probes, I got nothing. So that means that it allows current to flow in one direction and not the other. Now let's take a look at the bridge rectifier. We've got 4 round knobs on the top and 4 round knobs on the bottom. The round knobs are the diodes, but we only have a total of 6 diodes. Here we have 8 round knobs. So let me show you the actual diodes here. You can see the round knob, and then it has a wire that goes down, and that wire is this wire right here. So that's the other end of the diode. So top diode here, and that's the bottom of the diode. And there's one here, there's one here. Those are the 3 diodes. The 4th round knob, which is this one here, is nothing. And also same thing on the bottom. So there are 4 round knobs, and each of the round knob is a diode. So this is one here, that's another one here, and then there's nothing here, and then that's the 3rd one here. And let's test the first 3 diodes on the top here, and the one end of the diode, they are all connected together on the piece of metal here on the top. The other end of the diodes, they go down and connected to this terminal here on the bottom, here, here, and here. The top part of the diode, they are connected together to this piece of metal here, and this piece of copper is connected to the metal frame of the alternator. So that is ground, which is here on the diagram. So I'm going to connect the positive of my multimeter, which is set to diode, and I'm going to connect it to ground, which is this piece of metal right here. And then I'm going to use my negative probe to test on the bottom of the diodes. Got half a volt, that's good. Half a volt on the second one, and on the third one, half a volt. So all the diodes are good, and this is an equivalent of testing from this point here on the positive, this point here on the negative probe, and they are all good. I'm going to reverse the polarity of the probe on my meter to test it again to make sure the diodes only allow current to flow in one direction and not the other. For the bottom 3 diodes on this rectifier, they are connected together to the positive terminal of the battery, which is this right here. And on the diagram, it is this point right here and goes to the positive of the battery. And the other end of the 3 diodes are the leg of the diodes, which are here, here, and here. So all I have to do is connect the negative probe on my multimeter to the main positive on the bridge rectifier, which is this point right here. And then I'm going to use my positive probe to test on the legs of the diodes down here. So let's try on the first diode, 0.5 volt, so that's good. Second diode, 0.5 volt, that's good. Third diode, 0.5 volt, so all 3 diodes are good. So on the diagram, this is equivalent as putting the negative probe on here or here, same thing, and then the positive probe on here, here, and here, and they all turn out to be 0.5 volts, which is good. Now let's do the test again, but this time in reverse, to make sure that the diode only allows current to flow in one direction and not the other. So these are the 3 diodes here. I got the positive probe on my meter and connect on here, and the negative probe will go on the leg of the diode. First one will be this one here, nothing. Second diode, nothing. Third diode, nothing. So all 3 diodes are good. So there you have it. I have completed my test with every single component on this alternator, and in this case it turns out to be worn out brushes, which is a very common problem with all of these alternators, and it should be the first thing that you should test if you have a bad alternator. And the last thing I've got to do is to put everything back together and put the alternator back in my car and test it and make sure that it works as it should. Okay, that's it. Alright, moment of truth. I put everything back together, and now I've got my amp meter to measure how much current. It's going to charge the battery, and my battery is right now at 12.56 volts. Alright, start the car. $14.1 volt. So it's charging the battery. Let's see what we got here. 21 amps. It's charging the battery at about 20 amps right now. 14.19 volts. It's working beautifully. And there you have it. It's quite a simple fix once you understand how this works. If you have any other tips in repairing the alternator, please write down in the comment below. It's going to help other people as well. And that's all I have for now, folks. Thanks for watching. See you next time.